Hi, this is Vaishnavi. Now I bring a topic among you is RIC and CIC architecture. We will compare the architectures now. Let's think about this means and which methodology, if either, is superior. For a long time, PCs with an Intel Central Processing Unit inside made use of the so-called x86 processor architecture. This type of processor employed the CIC methodology. Apple computers, on the other hand, were based on the ARM processor architecture. ARM stands for Advanced RISC Machines, and needless to say, they employed the RISC methodology. These days, you could say that x86 and ARM processor have evolved towards each other, and now they both have features of RISC and CISC. To understand the features of RISC and CISC, let's first consider the anatomy of an assembly language instruction and therefore a binary machine code instruction. Here are some examples of assembly language instruction in no particular language. In the early days of computer, this is the kind of code programmers used to write. These instructions make use of mnemonics such as load, store, and halt, and they use symbols to represent memory address such as X, Y, and Z. This program loads a copy of the contents of memory location X into CPU's accumulator. It then adds a copy of the content of memory location Y to whatever is in the accumulator, then stores a copy of the result back into location Z. Finally, the program stops. Not many people write low-level assembly code like this anymore. High-level programming languages means that programmer no longer have to think in terms of CPU registers like the accumulator. Nevertheless, when high-level code is compiled, that is, when it is translated into binary machine code, it may well pass through an intermediate form of code that looks rather like this. One of the key features of an assembly language instruction is that it corresponds to exactly one binary machine code instruction. When the program is translated into a machine code, there will be 4 machine code instructions. Furthermore, the anatomy of an assembly language instruction is the same as that of machine code instruction. Each instruction here includes a operation code and an operand except for the final halt instruction, which does not need an operand. The operation code, often referred to as opcode, is the operation to be performed such as load, add, subtract, multiply, store, compare, jump, and halt. All of the possible operations that a particular processor can understand are known collectively as the processor instruction set. The operand is whatever is being operated upon. In this program, X, Y, and Z are operands. Each operand specifies a memory location where the data required by the instruction can be found. X, Y, and Z are actually symbolic representation of memory addresses. For this reason, the operand is sometimes referred to as the address field. Some instructions have more than one operand. A move or copy instruction, for example, will specify where to move or copy to followed by where to move or copy from. An instruction can also have a label so that a jump instruction can pass control to it when executing a loop, for example. There is no need to concern ourselves with the detail of any particular assembly language for the purpose of this discussion. Let's keep things nice and simple. Now, as I've already said, before they can be executed, assembly language instructions must be translated into binary machine code instruction first. Each operation has its own binary code and each operand is converted into a numeric memory address. The program is saved on a secondary storage such as hard drive as an executable file. When a program starts running, all of these machine code instructions are loaded into the computer's main memory, the RAM. One at a time, each machine code instruction is fetched from the memory into the CPU's current instruction register so it can be executed. Here, a simplified view of a machine code instruction inside the current instruction register. This is a 32-bit register. Each cell of the register is capable of storing a 1 or a 0. In reality, a register cell is actually an electronic circuit designed to latch onto an electric charge. If the cell is charged, it represents a binary 1. If it is not, it represents a 0. 8 cells of this register have been allocated to store the operation code. The remaining 24 cells have been allocated to store the operand. These allocations are fixed. They are hardwired into the processor. With 8 bits available for an operation code, this processor can have up to 2 to the power 8, that is 256 different operation codes in its instruction set. With 24 bits available for the operand, which remember is actually a memory address, an instruction can refer up to 2 to the power of 24 different memory address directly. That is over 16.7 million different memory addresses. But consider this, 16.7 million unique memory address is not that much. That's only about 16 megabytes of memory. For a fixed site current instruction register, how then can we increase the amount of memory that can be addressed by a program? One solution is to allocate more bits to the operand. This time 27 bits are available to specify a memory address, which means 2 to the power 27 different memory locations can now be accessed directly. That is over 134 million locations this time. But there is a price to pay. Now there are only 5 bits available for the operation code. This means 2 to the power 5, that's only 32 possible operations in the instruction set. This fundamental design decision, how many bits to allocate to the operation code and how many bits to allocate to the operand, is at the heart of the difference between RIC and CISC. A reduced instruction set computer allocates fewer bits to the operation code than a complex instruction set computer. Typically, a modern RISC processor has 70 to 80 instructions in its instruction set, whereas the CISC processor has a much richer instruction set of up to 150 instructions. So let's summarize the difference between RISC and CISC. Apart from the main difference, that is number of instructions available in the instruction set, there are others worthy of mention. A typical CISC instruction, as the name suggests, it is more complex than a RISC instruction. Typically, a CISC instruction can do more than a RISC instruction. For example, in a RISC architecture, adding 2 numbers together might require one instruction to load the first number into the accumulator, then another to add the second number to that. In a CISC architecture, on the other hand, it may be possible to perform the same task with just one instruction. Multiplying 2 numbers together with RISC instruction set may involve several instructions that repeatedly add number to itself within a loop. A CISC instruction set, on the other hand, might have a multiply operation. Because RISC instructions are less complex, more of them needed to perform a particular task. But because they are simpler, less clock cycles are needed to execute each instruction. A typical CISC instruction may be more capable, but it needs more clock cycle to complete. A RISC program is necessarily going to have more code than CISC program, so a RISC program will take up more memory. High-level programming languages comprise of RISC and CISC machines are different. When a programmer writes code in a high-level language such as a Visual Basic or C#, it's relatively easy to do because it's close to the way they speak. CISC assembly code is more similar to high-level code than RISC assembly code. This means that a compiler which generates machine code for a CISC processor is simpler and faster than that for a RISC processor. Some programs still write code by hand in assembly language because it allows for fine control of computer resources such as memory. If you think about it, RISC assembly programmers have to work harder than CISC assembly programmers. CISC processor chips are more complex than RISC processor chips. A single CISC instruction can achieve more because it relies on a more complex system of a circuitry and logic gates within the ALU unit. This means CISC chips are more expensive to design and to produce. One of the most important differences between RISC and CISC comes back down to the way that the bits of the current instruction register are allocated between the operation code and the operand. When more bits are allocated to the operand, a RISC processor can access more memory locations directly than a CISC processor. With fewer bits available for the operand, a CAC processor needs some way for an instruction to reach higher memory address that otherwise could not be accessed with direct addressing alone. This is achieved by employing various rules for interrupting the operand known as addressing modes. Addressing modes are described in detail in another video and suffice to know the machines need more of them. Now you already know that there is no simple answer. How quickly a processor can accomplish a task depends on a few things: the number of clock cycle per second, the number of clock cycle it takes to complete one instruction, and the number of instructions required to perform a task. Clock cycle per second is largely independent of the processor architecture, so it comes down to two factors. CIC processor achieves speed with a rich instruction set, so it takes fewer instructions to complete a task. RISC processor use more instruction for a given task, but less clock cycle are needed to execute each instruction. It would seem that there is no benefit of one over the other. So RISC is often used in high-end applications that require fast processing of a limited number of instructions, such as image, video, audio processing. CISC, on the other hand, is often used in low-end applications such as security systems and home automation. So based on the requirement, you choose the architecture. Thank you.